Hello, calculus students, and welcome to another day of coronavirus calculus, brought to you by Mr. Wyman. So, yesterday we were working with integrals involving powers of sine and cosine. Today we're going to work with integrals involving powers of secant and tangent. And we're going to have a new set of guidelines, but our goal is going to be the same. We're essentially going to want to get things so they're in terms of u du, so we can just apply the power rule. Okay, so for rule number 1, if the power of the secant is even and positive, save a secant squared factor and convert the remaining factors to tangents. And the reason you do that is because, well, just remember, if we want to get things into u du, if our u is tangent, well, the derivative of tangent is secant squared. So our goal is to save a secant squared factor and convert the remaining factors to tangents. So in this instance, we're going to have, well, this would be the same. The secant to the 2k of x times tangent to the n of x dx is going to be the same as the integral of secant squared x to the k minus 1. So at this point we have factored out a secant squared factor times tangent to the n of x secant squared x dx. Okay, so that's our first step. Basically take out a secant squared factor and then convert everything to tangents. So the secant squared x to the k minus 1, we're going to convert that to a tangent using a Pythagorean identity. That's going to be the same as the integral of 1 plus tangent squared x to the k minus 1 tangent to the, what is it, tangent to the n? Tangent to the n of x secant squared x dx. Okay, so once you get it there, you should be able to integrate it, basically distribute, and then get everything so you have a u du, or a tangent times a secant squared thing. Okay, so in rule number 2, if the power of tangent is odd and positive, save a secant tangent factor and convert the remaining factors to secants. And the reason you save a secant tangent factor is because, well, if you convert everything to secants, what's the derivative of secant? And the derivative is secant tangent. So if you want to get everything so it's a secant tangent, that way it's u du, and then basically integrate using the power rule again. So this is going to be the same as the integral of secant. Well, we're going to factor out a secant, which means we're going to have one less term here, times, well, we have our tangent to the second of x times k. And then we have, because we've technically taken out a tangent factor as well, that way we have a secant tangent. And then you want to convert everything so it's in terms of secant, except for that tangent that's attached to the secant at the end. This is, again, this would be our u. And then this is effectively going to become our du, or excuse me, this is our du, mess that up, and this is going to become our u. But convert everything so it's in terms of secant, so that way you have the secant times the secant tangent form. So this is going to be, well, secant to the m minus 1 still, but then tangent squared, we know that the trig identity is going to be, well, or excuse me, yeah, the Pythagorean identity is going to be secant squared x minus 1 to the k still, times that secant x tangent x dx. Okay, now in rule number 3, if there are no secant factors, and the power of tangent is even and positive, we want to convert a tangent squared factor to a secant squared, looks like I left off some stuff, squared factor, and then expand and repeat that if necessary. Okay, so we have the integral of tangent to the n of x dx. What we want to do here, since tangent doesn't have some arbitrary antiderivative, we want to, well, convert, I guess tangent to the power doesn't have an arbitrary derivative, I should say. What we want to do here is, well, convert a tangent squared factor to a secant squared. So, basically factor out a tangent squared. So this is going to be tangent, well, if we factor out a tangent squared, that's going to be 2 less terms. So tangent to the n minus 2 x times, well, we've just factored out a tangent squared of x dx, and then convert that to a secant squared. So then we'll have a tangent to the n minus 2 times x times secant squared x minus 1 dx. And the reason you do that is because now we can basically, we have our u, we have our du, we know that the derivative of tangent is secant squared, and we can apply the power rule after some arithmetic. All right, example 4, if the integral is in the form secant to the mx dx, where m is odd and positive, use integration by parts. We cannot do that. We have not learned integration by parts. That is calculus BC. So we'll ignore that for now. Okay, if none of these first, 3 guidelines apply, we can always try converting to sines and cosines, and then using some anti-differentiation techniques we've learned. Okay, so these are basically, you're going to want to follow these guidelines. There's a couple more than with sine and cosine, but follow these guidelines, and you're going to really use that Pythagorean identity a lot, that tangent squared theta plus 1 equals secant squared theta plus 1, or whoops, not plus 1, just secant squared theta. Okay, so you're going to use that a lot. So in example 4 here, the power of tangent is odd and positive. Okay, well, since we have a tangent term, we have a secant term, and the power of tangent is odd and positive, that means we're going to have to apply the second rule, which tells me that I want to get everything in terms of secant and then save a secant tangent term. So let's just first rewrite the way this looks. This is the same as the integral of tangent cubed x times secant x to the negative 1/2. Okay, so what we want to do, and then dx, what we want to do is get everything in terms of secant, but save a single tangent term, a tangent secant. Okay, so what we have to do here is we want to save its tangent secant, so we have to factor out a tangent from here. We have to factor out a secant from here. So if I factor out a tangent, I'm going to have one less tangent from tangent cubed. That's going to be tangent to the 3 minus 1 is 2, so tangent squared of x. Now this is the one that kind of stumps kids. Just remember, if we're going to factor out a secant x, we're still taking out one secant, so we're going to subtract that power by 1. So it would be secant to the negative 1/2 minus 1, which is secant to the negative 3/2. And then we now, since we factored that out, we have this secant x, this tangent x. This is going to become our du. This is going to become our du, essentially, that dx as well. And what we want to do is convert everything so it's in terms of secants, and then this will essentially become our u. So let's convert these things to be in terms of secants. So tangent squared of x. Well, if you use the Pythagorean identity above, if we isolate tangent squared, we subtract one to the other side. We know that tangent squared is the same as secant, the integral of secant squared of x minus 1 times secant to the negative 3/2. And then we have that du, that secant x. We're just going to bring that along for the ride, secant x tangent x dx. This is going to equal, okay, now what we want to do here, basically get rid of that negative 1. So we're going to distribute secant to the negative 3/2 times secant squared. Well, 2 minus 3/2 leaves me with 1/2 positive. So this is secant x to the positive 1/2 minus secant x to the negative 3/2, doing the integral of this. And then we still have this secant x tangent x at the end. Okay, so at this point, I'm not going to really rewrite much. These, we can kind of look at these. We're taking secant x times secant x to the 1/2 times secant x tangent x. We're taking negative secant x to the negative 3/2 times secant x tangent x. So basically, this is our u. This is another u. And we're going to integrate these and kind of treat secant x as if it's our u, our negative secant x to the negative 3/2 as if it's u to the negative 3/2. This would be u to the 1/2. And then our du is here. So we can apply the power rule at this point. This is going to become the same thing as, well, if this is our u, we just add 1 to the exponent and divide by that quantity. So it'd be, well, u to the 3/2, but our u is, in this case, secant x. So secant x to the 3/2 divide by that quantity, which is 3/2, or that's the same as multiplying by 2/3. We'll simplify in the end here. Then we're subtracting, well, u to the negative 3/2, add 1 to that quantity. That's u to the negative 1/2. Well, that's secant x to the negative 1/2 divided by that same quantity, divided by negative 1/2. Okay, we'll clean this up at the end. Then we are doing a indefinite integral, so we have that plus c. This is all equal to, simplify, this is the same as 2/3 secant x to the 3/2. Okay, minus, and then we're dividing by -1/2. That's the same as multiplying by -2. Negative times negative is a positive, so positive secant x to the -1/2 plus c. If you want to rewrite these as radicals, that's fine, but you certainly, if you want to write the negative in the denominator, that's fine too, but you certainly don't have to. I would probably accept this at this point. This is just fine. Okay, so that's how you tackle example 4. Example 5, the power of secant is even and positive. The power of secant is even and positive. Now, hold on. Why did the book do integration by parts? Give me 1 second. Example 5, I'm going to leave for you to work out on your own. You could notice that the power of secant is even and positive, but the power of tangent is also odd and positive. So which rule would you use? And technically you could use either rule. You could use rule 1 or guideline 2. And I'll leave that as an exercise for you guys to work it out. This example's in your book. You can always hop on the Zoom meetings, and I'll certainly help you out if you have questions on that one as well. Okay, but we're going to move on. I'm going to leave that one for you guys to work out on your own. Example 6, when the power of tangent is even. Okay, well, when the power of tangent is even, but what else do you notice? There is no secant factor. So this is going to be guideline number 3 here. And what we want to do in this instance then, is since there are no secant factors and the power of tangent is even and positive, we want to convert a tangent squared factor to a secant squared factor. That way, we can do the u du and then basically have a power rule. Because remember that the derivative of tangent is secant squared, so that's our u is going to be tangent, our du is going to be secant squared. So we're going to first convert this to a tangent squared factor and then apply a Pythagorean identity. So this is the same, and what I'm going to do actually, this is the same as the integral from 0 to pi over 4 of, well, if I want a tangent squared factor, I'd be left with the tangent squared of x times the tangent squared of x dx, but I really only want one of these initially, and then convert one of those to a Pythagorean identity. So this is the same as the integral 0 to pi over 4 of tangent squared of x times, well, tangent squared, the Pythagorean identity tells us that's the same as secant squared of x minus 1 dx. This is going to equal, again, 0 to pi over 4 of, okay, now I'm going to distribute that tangent squared, so it's going to be tangent squared of x times secant squared of x minus this integral of, and then I'm left with secant squared x minus 1. Okay, now why would I split that up? And then I get the dx at each of these. Whoops. Okay, and the reason you split these up is because, well, this tangent squared secant squared, the way we wrote this is, remember that if tangent is u, just that tangent term, well then our du becomes secant squared of x dx, which is right here. So essentially we have u squared du. We have u squared du. Okay, so, well, the antiderivative of u squared du, well, you add 1 to the exponent, so it's u to the third, or tangent to the third of x, and then divide by that quantity, so divide by 3. Okay, now here, what is the antiderivative? We're going to have to take the antiderivative of secant squared of x and the antiderivative of -1. And sometimes kids kind of lose their train of thought. Well, what's the antiderivative of secant of squared? Well, look up here. We said tangent, if u is tangent of x, what's the derivative of tangent? Secant squared. Well, if the derivative of tangent is secant squared, what's the antiderivative of secant squared? It's got to be tangent. So the antiderivative of secant squared of x is going to be, well, minus tangent of x Then the antiderivative of -1 is negative x, but we're subtracting that quantity, so it's minus negative x or plus x. And this is a definite integral. We are evaluating all of this from 0 to pi over 4. Plug that into your calculator. You're going to get pi over 4 minus 2/3, which is approximately 0.119. That is our answer. Okay, so what happens then if we can't do any of the first three guidelines? So we want to look at this example, secant x dx over tangent squared x. Well, if the power of secant is even and positive, well, that's not going to apply here. It's odd and positive. Well, what about the power of tangent? That is even. It's even and positive. But for that rule, that would be rule number 3 like we just did, we can't have a secant term, so that doesn't apply. And we don't have a power of tangent that's odd and positive. So none of the first 3 rules apply. What we want to do here is convert this so it's in terms of sines and cosines. So this is the same thing as the integral of, well, secant. We know that the reciprocal identity there is going to be, well, that's the same as 1 over cosine of x. All of that divided by, well, tangent squared is the same as sine of x over cosine of x squared. Okay, well, I'm dividing by 2 fractions. This is the same as multiplying by the reciprocal. This is the same, dx there. This is the same as the integral of, well, 1 over cosine of x times cosine of x squared over sine of x, all that whole quantity squared dx. Okay, now what we can do here is we're multiplying these 2 fractions. This would be the same as multiplying a cosine of x squared over a cosine of x. Well, cosine x squared over cosine x, that's just going to reduce to, I guess I'll write this so I don't lose too many people. This is the same as, well, I could write this as cosine squared x over cosine x, and that would leave me with 1 over sine squared of x dx. Okay, well, cosine squared over cosine, that's just going to become the integral of cosine of x times, and the reason this works out nicely is because this becomes, well, sine 1 over sine squared. That's the same as sine of x to the -2 dx. And basically, you can recognize we have a power rule now. But what's going to be my u? Basically, this is kind of like a chain rule, sort of, with these trig, sines and these cosines. This is going to be our u inside the parentheses. This is going to be our du. This is our du. So if you really wanted to, you could just replace this. This is the same as saying u to the -2nd times du. Okay, and the reason that, I guess this du needs our dx here, move that over, then it would be our true du. But if sine of x is our u, well, what's the derivative of sine of x? The derivative of sine of x is just positive cosine of x, so we're good there. It's just u to the -2nd du, integral of that, which we know, well, our u is sine of x, so add 1 to the exponent, it's going to be sine of x to the -1st, divide by that, divided by -1, and then plus c. Okay, well, we can rewrite this a little bit further. Dividing by -1, that's the same as multiplying by -1. So this is technically negative sine of x to the -1st, which is the same as 1 over sine of x. And we know that that is the same as, write it down here, plus c. 1 over sine is the same as cosecant. So this is negative cosecant x plus c. So that's an example. If none of the first 3 rules apply, try and convert to sine and cosine factors and then integrate using strategies you've done before. Okay. Integrals involving sine, cosine products with different angles. So we're going to need this information for the last one. And when we have integrals that involve the products of sines and cosines of 2 different angles, we want to use product to sum identities to kind of rewrite these things and then integrate from there. Okay, so I'm going to you have those in your notes. I'm going to rewrite them. They're going to look just a slightly bit different than the one that's in your trig cheat sheet. Okay, but they're the exact same thing. So when, I guess I'll write that down. when integrals involve products of sines and cosines of two different angles. Yeah, goodness, I'm running out of room there. Of two different angles. We want to use product to sum identities. And then kind of integrate from there. So our product to sum identities, if I have sine of some m times x times sine of some n times x, that's going to be equal to 1/2 times cosine of the difference in those values of x minus cosine times the difference in those values, or excuse me, plus those values of x. Okay, if I have sine times some angle of x times cosine of some other angle of x, angle times x, equals 1/2. This is going to be basically the same structure, but sine plus sine. So this is going to be 1/2 times sine, and I guess I needed a parenthesis up here. Whoops. 1/2 times sine, and then the difference in those angles. It's always going to be the difference in those first. Okay, now plus sine times the sum of those angles. It's always going to be the sum of those angles at the end. N times x. And our last case, cosine. If I have cosine of two different angles, cosine m of x times cosine n of x, that's going to be equal to 1/2 times cosine of the difference of those angles times x plus cosine of the different, or of the sum of those angles times x. Oops. Wait, no, we're good. Gosh, I'm just missing brackets everywhere here, aren't I? Alright, now we're good. So we're going to want to use these product to sum identities, rewrite them, and then kind of integrate from there. So if we have the integral of sine of 5 of x cosine 4 of x dx, well, we have two different angles. We have a 5 and a 4. So we want to apply, well, we have sine cosine, so that's going to be the middle one. We know that this is the same as 1/2 times sine, the integral of 1/2 times sine of, well, 5 minus 4x plus sine of, goodness, my parentheses and my brackets, I'm not doing so well with those. All right, plus sine times the sum of those, so 5 plus 4 of x. I kind of did it backwards, that's all right. 5 plus 4 of x, and then we need our dx at the end of all of this. All right. Just clean that up a little bit. This is going to be the same as, well, 1/2. We can bring that out front. It's a constant. That's 1/2 times the integral of, well, 5 minus 4 is 1, so this just becomes sine of x, plus 5 plus 4 is 9, so that becomes sine of 9x dx. Okay, well, the antiderivative of sine of x is cosine, or excuse me, the antiderivative of sine. Well, what thing's derivative gives me positive sine? Well, we know cosine is negative sine, so it has to be negative cosine. So this becomes 1/2 times negative cosine of x. All right, now sine of 9x, that's kind of like a chain rule here. Since we have 9 times x, this is technically where it would normally be like, we should see 1/9, or we should see 9 times sine of 9x, right? Well, if we did see 9 times the sine of 9x, we would know that the antiderivative would just be cosine of 9x, or excuse me, negative cosine of 9x. But we do not see that 9, which means it should have something there, and we're saying, well, what times 9 would give us 1? And it would be 1/9. So this is going to be 1/9 cosine of 9x. We're kind of reversing that trig identity chain rule, but keep in mind, well, double check. If I did the derivative of 1/9 cosine of 9x, I would get, well, the derivative of the outside with respect to the inside would be negative 1/9 sine of 9x, and then times the derivative of the inside times 9, so 1/9 times 9, that would reduce, but we should have a negative here. So it should be minus 1/9 cosine of 9x plus c. We have evaluated that integral. And I guess I would always recommend just double checking these. Just differentiate and make sure that you did the derivative correctly, because sometimes reversing those chain rules is kind of tricky. So make sure you're doing those properly. All right, but we can just simplify these things. 1/2 times negative cosine of x, that's the same as negative cosine x over 2, or if you want to just leave it as 1/2 times that quantity, that's fine, negative 1/2. Okay, now 1/9 times 1/2, we're going to have minus cosine of 9x over 18 plus c. And that's all we're going to have today. As always, make sure you guys are practicing in your progress packet, and stay safe out there.